Welcome to this explainer. I am absolutely thrilled to have you here today because we're going to demystify the invisible architecture that literally runs our entire digital world. We're talking about the TCP/IP model. So whether you're studying for your CCNA, maybe you're a software developer, a systems administrator, or just someone who's super fascinated by how information moves from point A to point B, you are absolutely in the right place. Let's just dive right into this. Have you ever actually stopped to wonder how billions of devices, smartphones, servers, laptops, smart TVs, how do they all just seamlessly communicate with each other? Like, how does a single tap on your screen manage to travel across oceans, blast through fiber optic cables, and then return as a fully loaded web page in just mere milliseconds? It's honestly a modern miracle, right? And the crazy part is, it's all orchestrated by this highly structured digital postal system.
And that digital postal system? Well, that's TCP/IP. It stands for Transmission Control Protocol and Internet Protocol. Now, the easiest way to think about this is to break it down. Think of the IP part as the addressing system. It's the thing that decides exactly where your package needs to go. TCP, on the other hand, well, that's your tracking and guaranteed delivery system. It makes sure your package arrives completely intact, in the exact right order, and with zero missing pieces. Together, they basically form the fundamental communication language of the entire Internet.
Okay, so here's our roadmap for today. We're going to start at the top with the application layer, then we'll move down to the transport layer, navigate through the internet layer, and finally hit the network access layer. Oh, and we'll wrap up by doing a quick comparison of TCP/IP against the OSI model. All right, section 1, the application layer, the interface. So you can really think of the application layer as the Internet's storefront. It acts as this vital bridge between human applications, like the web browser you're using right now, or your email client, and all the complex network data that's swirling around behind the scenes. When you want to do something online, this layer steps in and translates your human actions into standardized network requests that the rest of the system can actually understand. And there is just a massive variety of protocols operating right under your nose here. When you're browsing the web, you're using HTTP, or its secure encrypted cousin, HTTPS. Sending an email, that's going to be SMTP. Fetching an email, that's IMAP or POP3. And then, there's DNS, the domain name system. DNS is absolute magic. It translates those human-readable names, like Google.com, into the raw numerical IP addresses that computers actually use. That way, you and I don't have to walk around memorizing huge strings of numbers just to check the news. Let's look at a quick real-life example of how this works. Say you type google.com right into your browser. Instantly, DNS kicks in to resolve that domain name into an IP address, something like 142.250. whatever. Then, an HTTPS request is generated to securely ask the server for the website's data. And the wild part? All of this happens right here at the application layer before your data even begins its journey downward through the stack. Moving right along, section 2, the transport layer, end-to-end delivery. If we're sticking with our postal metaphor, think of the transport layer as the ultimate logistics manager. It takes the data from that application layer we just talked about and literally slices it up into smaller, much more manageable chunks called segments. But more importantly, it ensures these segments actually reach the correct specific application on the destination device. And it does this using port numbers. So if IP addresses are like the street address of a big apartment building, port numbers, they're the specific apartment numbers. Like port 80 is specifically for HTTP, port 443 is for HTTPS, and so on. Now, right at this layer, the system has to make a pretty crucial choice between two main protocols, TCP and UDP. TCP, well, it's connection-oriented. It is highly reliable. It guarantees ordered delivery, and it is constantly checking for errors. Basically, if a segment gets lost, TCP is going to resend it. UDP, on the other hand, is connectionless, and because it completely strips away all that error-checking overhead, it is extremely fast. It literally just fires data at the target, there's no guaranteed order, and absolutely no resending of lost pieces. So to achieve that super strict reliability we just mentioned with TCP, it uses this brilliant mechanism called the three-way handshake. Before a single piece of actual data is even sent, the client sends a SYN, or synchronize, request. The server then replies with a SYN-ACK to say, hey, I acknowledge and accept this. And finally, the client sends an ACK to confirm. Boom. It's a digital handshake that establishes a really secure, reliable connection. And this exact sequence happens every single time you log into your bank account or open up a secure email. The crucial takeaway here is really knowing when each protocol is used in your day-to-day life. Stuff like loading web pages, sending emails, or downloading a file, You absolutely need TCP for that. I mean, you can't have a file missing half its data, right? But what about when you're playing an online game like PUBG, or you're watching a live stream, or you're on a VoIP video call? That is exactly where UDP shines. In those cases, a tiny blip or a dropped frame is totally fine as long as the stream stays lightning fast and in real time.
Okay, Section 3, the Internet Layer, Global Routing.
So, down we go to the Internet layer, which is essentially our global postal routing system. See, while the transport layer was all concerned with application-to-application delivery, the Internet layer is solely focused on network-to-network delivery. What it does is encapsulate those segments we made into things called packets. It stamps them with a source and a destination IP address, and then it uses routers to figure out the absolute best physical path across the entire world's interconnected networks.
And the undisputed star of this layer is, of course, the IP address. Historically, we've relied on IPv4, which uses these 32-bit addresses. You've probably seen them, like 192.168.1.1. But here's the problem. That structure only gives us about 4.3 billion unique addresses, and honestly, we basically ran out. So that's exactly why IPv6 was developed. By utilizing a massive 128-bit structure, IPv6 is totally future-proof. It provides enough unique addresses for literally every single device we could possibly invent.
Let's take a quick look at the core protocols at work here. First, we have IP, which addresses and routes those packets. Then we've got ICMP, which handles all the error reporting. Actually, if you've ever opened up a command prompt and typed ping just to see if a website was online, you were using ICMP right then and there. And finally, there's ARP. ARP is super vital because it bridges the gap downward. It translates those logical IP addresses we've been talking about into the actual, physical MAC addresses of your hardware. Let's map out a real-life journey for a second. Imagine you're sitting in Istanbul and you're requesting data from a server located in the United States. Your machine creates an IP packet. Then, your home router sends it over to your internet service provider. From there, a massive complex chain of international routers reads that destination IP and just hands the packet off, hop by hop, across whole continents and deep underwater cables until it arrives at that exact server in the US. The efficiency of it is just astonishing. Which brings us to the bottom of the stack. Section 4, the network access layer, physical links. This is it. The network access layer is where the digital finally meets the physical. Because think about it, all those logical packets and ports, they mean absolutely nothing without actual physical delivery. This layer takes our digital data and turns it into physical reality. We're talking the asphalt on the road, the delivery trucks, the electrical signals in copper cables, the light pulses in fiber optics, and the radio waves of your Wi-Fi. It manages communication purely within the local network. Let's break down how this actually builds our local connection. At this deepest layer, the IP packet is encapsulated one last time into what we call a frame. Now, this frame uses MAC addresses. Those are the unique 48-bit physical IDs that are permanently burned right into your network card. Devices like network switches read these MAC addresses to direct traffic locally, whether that's over Ethernet cables or Wi-Fi. The frame also includes a CRC, which is basically just a mathematical check to guarantee that not a single bit got corrupted while traveling over the physical wire or through the air.
To make this a bit more concrete, just imagine you're sending a document to your local network printer. Your PC already knows the printer's IP, but it uses that ARP protocol we mentioned to find the printer's physical MAC address. A frame is then built containing your document. That frame hits your local network switch, the switch looks at the destination MAC address, and boom! It forwards the frame exactly to the physical port where your printer's plugged in. And the coolest part? This entire interaction happens completely at the network access layer. It never even touches the wider internet.
All right, last major topic. TCP/IP versus OSI model. Comparing standards.
So, if you're studying networking, you've definitely seen the OSI model. It's a 7-layer theoretical framework that's used heavily in education. But TCP/IP, that is the actual working model of the internet. And just look at how beautifully TCP/IP simplifies things here. The top 3 layers of OSI, application, presentation, and session, they're all consolidated into the single TCP/IP application layer. The transport layer, that remains a nice one-to-one match. OSI's network layer becomes the TCP/IP internet layer. And finally, those bottom 2 OSI layers, data link and physical, are seamlessly combined into the TCP/IP network access layer. It's just a much more practical, streamlined approach to the whole shebang.
Think about this for a second. From the application storefront all the way down to the physical pulses of your Wi-Fi, billions of devices are executing this incredible 4-layer encapsulation dance in milliseconds every single time you click a link. It is just a breathtaking feat of human engineering. So, now that you really understand the blueprint, from ports and TCP handshakes to IPs and MAC addresses, how differently are you going to view the digital world the next time you connect? Thank you so much for exploring this explainer with me today, and as always, keep learning.